Hi everyone, welcome back to Math 112. This is Scott. Let's get started. What we are going to be talking about today is section 5.5, where we build on our knowledge of the trigonometric functions and figure out some things about the graphs of tangent, cotangent, cosecant, and secant. Alright, so let's just start with tangent. And we'll just think about this in terms of the unit circle. So the tangent represents the slope, essentially, of the ray that rotates around the unit circle in the standard trigonometric orientation. So that would be starting at the positive x-axis and going counterclockwise. And if we think about what's going to be happening with that slope, so when the angle is 0, the slope will be 0. When the angle is positive, like this, it will start out getting steeper and steeper and steeper slope until we reach the time when it's actually vertical, at which point the slope will be undefined, and then it will start to have a negative slope, and it will become less and less steep, back down to 0, and then eventually it will become undefined again, and then it will be, let's see, so over here it'll be positive again. Here it will be negative again. And effectively, what we would be doing if we were to trace that all out is, so the basic shape will be, essentially it looks kind of like a heart monitor. Like a heart monitor in a hospital. So every time we have we were at the top or bottom of the unit circle, that's going to be a vertical slope, which means we're going to have a vertical asymptote. So that would be at pi over 2. It would be happening again. Let's see, in here, and then happening again at 3 pi over 2. That should be a little bit more evenly spaced here. And again, one more time at 5 pi over 2. And then negatively, if we go backwards, we can see that it will be the same thing again at the negative versions of each of these. Tangent, remember, is an odd function, which means that the vertical asymptotes will be basically symmetrically scattered around the y-axis. So negative pi over 2. And here, those are all spots where we can see the slope will be 0. And here the slope will be negative. And then the slope will be positive. Slope will be negative. And then the slope will be positive. Slope will be negative. Slope will be positive. And these values would be at pi, 2 pi, 3 pi, and so on. So, other important facts. So let's say we were taking the first period. Remember, the period of tangent is only pi. So let's just say we're taking the first period here from here to here, or else from negative pi over 2 to pi over 2, either way. If we look at the quarter periods, so the first and third quarter periods, that would correspond with 45-degree angle on this one and 135-degree angle over here. And in either case, the tangent at those points would actually just be 1 or negative 1. And what that means is that we actually have something to help us scale our graph. So that would be at 1. And here, at this point, this will be at negative 1. All right. So some of the features that we can notice here. Features. There are vertical asymptotes, there are vertical asymptotes at the middle of each cycle. There are x-intercepts at the beginning and end of each cycle, and here I mean starting at x equals 0, and again here starting at x equals 0. So those are two facts. And then the period is pi, and at the first and third quarter periods, the y value is 1. Okay, and those are some of the important things. Also, the range. So remember, range is all the y values that are ever reached by the function, and we can see that the y values go infinitely up, infinitely down. So the range is all real numbers. And that's basically the important features of the tangent function. Now, if we do any function transformations, those will affect the spacing of the things that we've just mentioned, but not the fundamental behavior. So transformations. So if we have y is equal to a, it's capital A, times the tangent of omega x plus b, then what this will do is each of these three parameters, the a, the omega, and the b, will each make a very predictable impact on the graph. Namely, the a will stretch the graph. So a, this is the vertical stretch factor. So the vertical stretch factor, and the effect of this, so the effect is that it changes the first and third quarter periods, how far those go from the midline. So the effect is the y values, so the values at the first and third quarter period are stretched away from the midline a units. Okay, omega. So this is sometimes called the angular velocity or the frequency or angular frequency. So this affects the speed of the graph. So this is the, we'll just call it angular velocity. That's one of the more common terms for it. And a higher value of omega is going through the angles faster. A lower value of omega is going through the angles slower. And the effect of it is that it shortens or speeds up the period. So the period is t equals, and ordinarily with the sine and the cosine we have 2 pi over omega. Here, because tangent as well as cotangent have periods of only pi, it's actually just going to be pi over omega. And then this means the quarter period key points will be every 1/4 t, which is 1/4 pi over omega. And these are the key points that we will use to help us lay out the graph. And then finally, the last of the three parameters here is the b, and the effect of the b is just it's just a vertical shift. And the effect so the effect of the vertical shift is just to change the midline. So the midline will be at y equals b. Okay, so that is the deal with tangent. Now we went in some detail about it, but let's now look at cotangent, and we won't go quite as in depth. We'll just think about what the relationship between them is, and we'll use that to glean the important information. So the cotangent. So this is the reciprocal of tangent. So that's going to be our easiest way of thinking about it. So let's just think about the basic graph. So if we think about what the basic graph of tangent looks like, so the basic shape of tangent looks like this. So wherever we have a y value of 0, that's going to correspond to a vertical asymptote. So essentially, the positioning of the vertical asymptotes and the y-intercepts are completely swapped. And as far as positive versus negative, wherever tangent is positive, the cotangent will be as well, and wherever tangent is negative, the cotangent will be as well. And what that actually is going to end up meaning is we have a giant positive y value, because it's a vertical asymptote, and then a giant negative y value, and then it repeats. So the vertical asymptotes from tangent become the y-intercepts of cotangent and vice versa. And as far as everything else, they are all just a modified version of the same information from tangent. So this was pi over 2, this was pi, this was 3 pi over 2, this was 2 pi, and this was negative pi over 2. And then furthermore, if we take the first and third quarter points, those will again be at the y values of 1 and negative 1. So so all of the important features are basically the same. It just has a sort of different orientation in the way the graph is drawn. So the basic features are pretty much the same. So the basic features are similar to tangent. Just the important thing is that the positioning of the x-intercept and the vertical asymptotes are switched. So the features are similar to tangent, except that the position of the x-intercepts and vertical asymptotes are switched. And the same thing happens when we do transformations to the cotangent as for tangent. So the transformations affect cotangent similarly to tangent. All right. So we won't belabor that anymore at the moment, and we'll move on to cosecant and secant functions. Now, the key to understanding the cosecant and the secant functions is to remember that they are both reciprocal functions for the root functions of sine and cosine. Graphs of cosecant and secant. So the basic idea here is to sketch the sine or cosine that the function would be based on. So give a rough sketch of the corresponding sine or cosine function. And then wherever the sine or the cosine hits its midline, in other words, if there's no shift where it has an x-intercept, that's where the function, the cosecant or secant, will have a vertical asymptote. So there will be a vertical asymptote for each point where the sinusoidal, that's sine or cosine, so where the sine or cosine crosses its midline. And then just draw, we can just say horns. On the top and bottom of each hump of the sine or cosine. And here I'll show you what I mean. So for cosecant, so we start by very gently drawing in the sine. So important facts are the amplitude, if we have not done any kind of a vertical stretch, will just be 1. And then the sine, let's say that's 2 pi. So that would be 4 pi. 6 pi. Negative 2 pi. Maybe it's a little bit, somewhere in between. All right, anyway. So the most important thing when you're sketching this out, especially if you're just doing it on an unlined piece of paper like this, is try to keep the spacing as consistent as you can, because that'll make all the difference in the quality of the graph. So okay, so let's see here. Now just mark out quarter periods, that's where the key points will be. And for sine, the way it's going to work is it goes to like that, 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 like that. And then what else we have here? We have one down here, right there, right there, and then up there. Okay, and then just very, very lightly sketch in the sine. Okay. So there we go. A very rough sketch of the sine. Now, wherever this crossed its midline, which would be at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and then on the negative side, negative pi and negative 2 pi, and so on. So in other words, every integer multiple of pi is another way of saying that. So every positive or negative whole number multiple of pi will have vertical asymptotes. And now what we do is we draw the actual cosecant by just taking right here and just drawing it like so. Just give. So it's these upper and lower. So basically, they're hyperbolas. It's these upper and lower hyperbolas that are going to be the graph of the cosecant. Oops, got a little bit cramped there. So this is the graph of cosecant. It's the humps that are both up, or it's the swoops that are both above and below the x-axis. Now, what does that then mean about the domain and range? So the domain of the cosecant here, the easiest way of expressing that is everywhere except where the vertical asymptotes are. So everything except the vertical asymptotes. So then how do we translate that into math? Well, it would be the set of all x such that, and you can do a bar or just a colon. So the set of all x such that, and then the way we express this is x is not equal to k pi, where k is any integer. So this is what's called set builder notation, and the way it's laid out is you give the name of the thing and then any conditions that apply to the thing. So x can be any value except any integer multiple of pi, because that's where sine has its x-intercepts, and therefore that's where the reciprocal of sine would be undefined. So k is any integer. Integer, so that is a Latin word. It means whole. So like the integrity of a building is its wholeness, and an integer is a whole number, and that includes the positive and negative ones. So that's what the domain of this function would be. And now, as for the range, so this is going to be everything above and below the sign. So these are, so we're always going to have a piece above and a piece below in all of these cosecant and secant functions. So here it's going to be, so it's going to be y is less than or equal to -1, or y is greater than or equal to 1. This is the way the ranges will always look. It's always going to have two pieces. It's going to have the piece that is from 1 up and the piece that is from -1 down. And we're saying anything that we call y could be in the range as long as it is either more negative than -1 or more positive than +1. And the secant we would approach in pretty much the same way. You just start by graphing the cosine, and then you would basically plot out where the vertical asymptotes would be, and then draw like little devil horns on the graph. So let's start with just the cosine part. So I'm going to draw this one a little bit smaller because that other one took a long time. So -1 to 1, 2 pi, 4 pi, 6 pi, and then break it up. Oops, break it up, break it up. And it's easiest to break it up into fractions like this. Break it up into quarters by first halving it and then halving that. Okay, now let's just think about what cosine's deal is. So cosine starts at its maximum, then it goes down, down, up, up, down, down, up, up, down, down, up, up. Let's see, it was at its maximum, so going backwards here, Okay, and at every 2 pi it should be back as it started. Okay, so this is cosine, down, and up, and down, and up, and down, and up, down, and up. All right, so that was the legwork. of getting these put in, and now we just figure out where the vertical asymptotes will be, and they'll be every place where the cosine had an x-intercept. So if we think about that, well, first off, it's easier to just draw it and then figure it out. But where are those? So if we think about where these are each going to be, this is pi, this is 3 pi, this is 5 pi, this is negative pi. It is happening every, so it looks like it's on the half pies. And in particular, it's the half pies that are going to be happening. So the vertical asymptotes will be happening at x equals, so pi over 2, 3 pi over 2, 5 pi over 2, and then the same for the negative, so we can just do plus minus, plus minus, plus minus. So odd multiples of pi over 2. Okay, so now let's actually just graph our secant here. So it's the part that's going to swoop above, swoop below, swoop above, below, above, below, above, below, above. So the graph of secant would be that part and that part. So the little cosine that we drew in between was just for our benefit. The actual graph of the secant is those swoops above and below. So then, the domain. So the way we can say this is, it is the set of all x such that x is not equal to k times pi over 2, which we can generally just write like this, where k is any odd integer. So that would be the way of wording that. And as for the range, it's going to be set of all y such that y is less than or equal to -1 or y is greater than or equal to +1. So again, it's everything outside of the band -1 to 1. Okay, so the only thing left to consider is what if we have transformations of the secant or cosecant. So we would just apply any transformations of the cosecant or secant to the root function first, so in other words the sine or cosine, and then proceed as above. Okay, so enough talk. Let's just try some examples. We'll just try one example for each of the categories of functions. So sketch the graph. And give the domain and range. Okay, so we'll just see just something from each category. So we'll go y equals 2 tan 3x plus 1 to start with. So we'll start with just a tangent, and we'll just figure out what transformations have happened to it, and then just do those to the basic tangent graph. All right, so there's a vertical stretch by a factor of 2. So that's going to affect the quarter period points. So the first and third quarter period points, this tells you how far above and below the midline they'll be. Speaking of the midline, that's going to be at y equals 1. That's the shift from the one that we are adding. Now the omega here is 3, which means that the period is going to be pi divided by omega, so pi divided by 3, which means that the key points will be every 1/4 times the period. So in other words, every pi over 12. Okay. So let's just sketch out a couple of periods here. So that'll be first period, second period. And now what's a period? A period is pi over 3. And this period would be at 2 pi over 3. And then if we game it out, so other important things for tangent happen at the half and quarter periods. And let's go just back one. So it's going to be negative pi over 3. Okay, now other important pieces of information here. The midline is at y equals 1. So the whole thing has been shifted up by 1 off of the x-axis. So everything we were saying before about x-intercepts, things like that, those have all been shifted by a slight amount here. So y equals 1. All right, now the vertical stretch tells you basically on the quarter point how far above and below the midline does the function swing by the quarter points. So here it's going to go 2 above, 2 below. So it's going to go from 1 down to negative 1, and from 1 up to 3. Okay. Now, let's plot this out. So every half period, that's when tangent expects to see its vertical asymptotes. And at the start of every period, it is going through its midline. Now, the point of these other values here is to help us set the pace. There, I need a little bit more room up above it. So the point of these other points is to help us set the pace of the swings. Okay, and then where else? I guess one right here. Okay, so let's just try this. So this was going through its midline. So because of the shift here and the stretch, we end up with a very, very large slope on these tangents. Remember, we're going to the midline here. Alright, so now let's think about where we are finding our vertical asymptotes at this point, because that's going to be important for the domain. So where are we here? So this is going to be at pi over 6. Where is this one going to be? This one's going to be at, so another way of thinking about this is 2 pi over 6, 3 pi over 6. Or in other words, pi over 2. Then the next one here would be at 5 pi over 6, which actually it's just that. The one back here would be negative pi over 6, and so I think I'm seeing the pattern here. So the domain is a little hard to see sometimes, but especially when the denominators are different. But the easiest way sometimes is just find a convenient common denominator and write everything in terms of that and hope for the best. So the domain here is going to be the set of all x such that x is not equal to k pi over 6, where k is any odd integer. So it becomes a little hard to see sometimes on these. It's best if you can try to put it in a way that makes the pattern more visible. As for the range, for the tangent and cotangent, this is always a gimme. It's all real numbers. So you could write this if you wanted with the set notation blackboard bold R. Or in interval notation. Negative infinity to infinity would be the way that would be most commonly expressed. Okay, so that's tangent. Cotangent, very similar. Very similar. So let's see. Let's go y equals negative cotangent. That last one was 3x, so let's make this 1/2 x. And again, plus 1. It's a good midline. Okay, so vertical stretch. And we'll put quotes on that because it's not really a stretch, but that's what we were calling it. So -1, so in other words, a reflection is what's really going on. As for the midline, just like before, it is at y equals 1. Now the omega is equal to 1/2, which means then the period would be t is equal to pi. Remember, for tangent and cotangent alike, the period by default is pi, and so the omega that speeds it up or slows it down will go into that. So that would equal pi over 1/2, which you can rewrite that as multiplication by the reciprocal, or you can multiply the top and bottom by 2, either way, and that gives us 2 pi, which means the key points are going to be happening every 1/4 times 2 pi, which is equal to pi over 2. Okay. So let's see here. Important facts. Midline y equals 1. Period 2 pi. So ordinarily, the period of cotangent would have just been pi, but here it's 2 pi. And the halfway mark, quarter-way mark, be there and there. Okay, what else we got? We want maybe a negative, a little bit on the negative side. So it'll be a halfway mark there. All right, now cotangent ordinarily has its vertical asymptotes at the beginning and end of its period, the same place where tangent has its midline slash its x-intercept if there's no vertical shift. So there's that. Now cotangent typically would be going down, but because of the reflection, it's actually going up. And so what that means is we're going to be going, and we need, so down 1, up 1 from its midline is where the quarter points will be. So what that means is we are going down there, up here, down here, up here, and again, you can just modify it as needed to make it look better. Up here. Now, ordinarily, cotangents come down like a waterfall, but this one has a reflection, so that means the shape of it will be going like that. Instead of it going like that. Notice it's much less vertically stretched than our tangent was. But the overall shape of it is actually quite similar to a tangent because of that vertical reflection. Okay, now for the domain, we can see where the vertical asymptotes are going to be, and they're going to be wherever x is at a multiple of 2 pi. So set of all x such that x is not equal to 2 pi k, where k is any integer. As for the range, all real numbers. All right. Now, C. So let's try something in the secant and cosecant family. Let's go y equals -2 cosecant. Let's go pi x plus 1. I like those midlines of 1. It's just enough for you to see what's going on with midlines. Okay, so now let's think about the vertical stretch. -2. So it's going to have a stretch of 2, but also upside down. Okay, midline, y equals 1. The omega here is pi, which means that the period 2 pi over omega, so this is not a tangent or cotangent, so it's going to be 2 pi divided by whatever the omega is. Just 2 pi over pi, which is just going to equal 2. And then that means the key points be every quarter period. So that's going to be every 1/2. Okay, now we start by just sketching the sine. Now the sine here is going to be a sine with a midline at y equals 1, a period of 2, which puts half periods at 1 and 3, quarter periods at 1/2, 1 1/2, etc. The amplitude is the vertical stretch here, so that's going to be, so this is y equals 1, so it means it's going to, the sine part is going to be going 2 up and 2 down. Like so. And so might as well go ahead and just put that in. It's important. It'll help us draw the sine properly. You can't draw a good cosecant if your sine is messed up. Okay, now other stuff. So, okay, this is the period, this is a full period. It's a upside down sine because of the fact that it is negative. It's going to be going down. Remember the midline is at y equals 1, so that's where it's going to be going up and down from. Okay. And then maybe back slightly here to there and there. Alright, so this is just the sine. This is all preliminary. We have not yet started the cosecant. This is just still some of the legwork. Okay, but now, wherever it crosses its midline, that's where we will find vertical asymptotes. And then we can actually draw the graph. So it's going to be the swoop above, the swoop below, the swoop above, below, above, and then below, above, below. Okay, so now the domain. So let's look at where we are spotting our vertical asymptotes. So it would appear that there's one at 0, 1, 2, 3, 4. So it would appear that x just can't be any integer. So the domain is everything that is not an integer. So the whole integer values are where we are finding our vertical asymptotes. As for the range, well, it's everything above the sine and below the sine. So it's a set of all y, such that y is greater than or equal to 3 or y is less than or equal to -1. So that's the amplitude up and down from the midline. All right, last one. Let's just do one example with the secant. All right, let's say just y equals secant x plus 2. Just nice and easy. All right, so the amplitude is just 1. Nothing funny going on. Midline now is 2. Omega is just 1, which means that the period is 2 pi over 1, which is just 2 pi, classic period. All right, and then the key points. Would be every 1/4 of 2 pi, which is pi over 2, which is just the default way key points are going to be. Okay, so there's our midline. That's our midline. Our amplitude is 1 for the cosine, so it's going to be 1 up and 1 down, so it's going to be 3 and 1. Okay, now period is 2 pi. Which means we've got half periods at pi, at the odd pi's, and then quarter periods at the half pi's. Okay. Cosine starts at its max. Oops. Getting a little sloppy on my cosine there, oh well. Because the important thing is not the cosine, because that's not what we were asked to graph, it's the secant. So now I put in the vertical asymptotes everywhere the function crosses its midline. And then I can actually draw the secant itself. Okay. Now for the domain and range. Alright, for the domain, I need to figure out where are we encountering, this was 0, 2 pi, where are we encountering our vertical asymptotes? So it would appear, sorry, this one is 0. So that's 0, it's 2 pi, so this would be pi, so it's going to be at pi over 2, 3 pi over 2, 5 pi over 2, etc. And then back here, negative pi over 2, etc. So that means the domain is going to be set of all x such that x is not equal to, and it looks like what we've got here, the pattern is odd multiples of pi over 2. So k pi over 2, k, any odd integer. And as for the range, these secant and cosecant ones, just figure out where the limits of the cosine will be, and you'll have the range for the secant. So it's a set of all y such that y is less than or equal to 1, or y is greater than or equal to 3. Okay. So that's the way you go about that. You start by plotting out the important things, like where you will find the vertical asymptotes and so on, how high up and down it will be at certain key values, and that'll be the process by which you will produce the graph. Now, let's have a look at what this is like in your homework. All right, so here I've brought up the Pearson version of your homework for section 5.5, and let's just see how the questions are going to go on this. So for these questions, it comes in two parts. The first ones are just sort of general questions, like what is the y-intercept of y equals tangent of x? And the best way to go about that would be to just draw yourself a quick little sketch of the function in question and use it to determine what is the answer to the question that you're being asked. So let's just say that this is pi, so the usual period of tangent, and just remind ourselves what's going on here. So we've got a vertical asymptote, and so and another vertical asymptote back here. And the graph of tangent looks like that. So the important thing is for y-intercept, it's asking you what y value does the function cross when x equals 0. And here from our quick sketch, we can see that the answer would be 0. And we can check the answer on that, and sure enough. Now, if we are asking instead about cotangent instead of tangent, we just quickly, once again, draw ourselves a quick little sketch to figure out what's going on. So again, pi. Now, the difference here is that the position of the vertical asymptotes and the x-intercepts are all switched around. So what that means is we've got a graph that looks like that. Now that means then that it starts with a vertical asymptote, and that means that there is no y-intercept. It never intercepts the y-axis. So that's how you would do that. Just sketch a quick graph and figure out from that. Now again, for secant, you just sketch a quick graph of that. Show you quickly, and if it was cosecant, you do the same. So for secant, it's all based on a cosine. So you just say, okay. So you just say, all right, cosine starts like this. Maybe it's like that, something like that. Okay, and that's good enough information for us because now we see where the vertical asymptotes are. And we can now draw our actual function, which is there. So y-intercept be right here, which is at 1. And you see, that's how that goes. All right, and then it asks again about cosecant, and very similar, just draw a sketch and try to figure out from there. All right, so now what it's asking is negative 2 pi to 2 pi. When does secant of x equal 1? Well, there are two ways you can do this. One is you can draw, again, a sketch of the function, or the other way might be to just look at the unit circle and try to figure out from that. So it's really your choice on this. I would say since we've been drawing these sketches so much, we might as well just stay on that. So let's just keep drawing sketches and make our decisions accordingly. Okay, so how would you answer a question like this? You would just sketch out the interval in question. This is just standard secant, no shifts of any kind, no stretches of any kind, just regular. So just go negative 2 pi to 2 pi. So that would be, in other words, two full periods. And we just think about how the cosine would look over this period of time, and then correspondingly what the secant would be like. So cosine would be maximum, mid, minimum, mid, maximum. And then the same thing in reverse. Okay, so here's finally my cosine. There's a cosine. All right, now if it's the secant we are after, we need to figure out how the graph is going to look. We got some vertical asymptotes here, 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 and here, duly noted. And then the actual function itself would be going down like that, up like that, down like that, up like that, and over here like that. Okay. So between negative 2 pi and 2 pi, when does the secant equal 1? All right. So it says use commas to separate the answers as needed. And I can see that where I'm going to be equal to 1 is there, there, and there. So negative 2 pi, 0, and 2 pi. So that's how I would answer this question. So I would go negative 2 pi, 0, 2 pi. All right, so that's how that one goes. And let's just see what else is on the agenda. And then it asks again, when does it equal negative 1? You just look at your graph here and figure out what values those were as well. Actually, let's go ahead and answer that. So when does it equal negative 1? Well, let's see here. It's going to be down there and down there. So what values are those? That would appear to be negative pi and positive pi. So the half periods. So negative pi, positive pi. All right, so negative pi and pi. All right. Same sort of question, but cosecant, so you just do a very similar thing. And now, for what values to have vertical asymptotes, very similar thing, similar thing, similar. Now here is where we have the last category of question. So you are given a function, and then you're going to have to figure out which of the graphs that were shown goes with this function, and then figure out the domain and range. Okay, so let's think about what is important about this graph here. So we know that the vertical stretch is 7. That's the only thing that's different about it from regular tangent. So the period will still be pi. The midline will still be 0, but at the quarter points it will be at 7. So let's just have a look at if any of these manage to accomplish that. So first off, looking at this one appears to have a period of 2 pi. You can tell the period of tangent from here to here, and that's that's out of the running. It's already got the wrong period. So I'm not even curious about anything more about that one. All right, let's try this one. So zoom in, you can make it bigger until you can finally see what's going on. Okay, so what is the period on this one? By the look of it, it starts its first period right here and ends right here. I like its period, but it's upside down. Regular tangent is supposed to be going up. This one's going down. All right. Well, never mind then. Let's check C now. So now, is it going the right way? Yes. Does it have the right period? Let's see. So from 0, it finishes its first period here, which would be at pi. So the period is good. That's nice. And now we just have to figure out, does this have the proper stretch? So it should have a vertical stretch by a factor of 7. How does a vertical stretch work its way into a tangent? Well, we have here the vertical asymptote, and halfway between the intercept and the asymptote, we have the quarter points. So we have the odd quarter points. So the first and third quarter points, and those should be whatever the vertical stretch is away from the midline. So those are supposed to be 7, and they are 7. If this is 14, then this will be 7. So this is the one for us. So there's our graph. As for the other one, what's wrong with it? Let's just figure out what the problem is. It looks like it doesn't have the stretch. It's just got a 1 up here. Okay. Okay, now as for the domain, so we have to figure out, where are our vertical asymptotes? Well, by the look of it, if this is 2 pi, that would be pi. This would be pi over 2 then, 3 pi over 2, negative pi over 2, negative 3 pi over 2. So now I can see the pattern here. The pattern is that it is the odd multiples of pi over 2. So I just got to figure out which one of these does that. All real numbers, nope. X is not equal to k pi over 2, where k is an odd integer. I like it, but let's just look at our other options before we commit. C, x is not equal to k pi, k is an integer. Nope, that's not right. And it's not equal to k pi over 4, where k is an odd integer. Nope, we want the k pi over 2. So there we go, check that. And that's how we would do that. Similarly, and we also need the range. The range on all the tangents are easy, just all real numbers. Okay. And that's how these questions go. And then you have another question like this where it is tangent, but it changes the period by giving you an omega. And what else you have? Secant. Only it's got a stretch and it's negative, so you just got to figure out which of these is going that way. Cosecant, cotangent, tangent. You've got it all here. So that's how you are going to be doing these problems. All right. So that is how you do that. Thank you for joining me for this episode of Math 112. I'll see you next time. Till then, bye.